Hello, my name is Matthew, and I'm an application engineer here at Hawk Ridge Systems. Artec Studio is the premier software that goes with the Artec brand scanners. Within the software, we can process scans to generate a mesh file, edit the meshes with the tools, and even extract CAD data for reverse engineering. With Studio 16, Artec, like usual, has added several new tools and ways to process the data, making it stand out compared to many other scanning softwares. In this video, I'm going to go over not only these new features, but also the complete walkthrough of using the software for Artec scanners and the various tools within it. Regardless of the type of scanner you use or object you're capturing, Artec Studio processes and handles those scans pretty much the same way. Even though I'll be using one type of scanner, these steps can be applied to other various types of scanners that Artec has. With that in mind, I'll be using the Ava to scan a decorative chair, a popular usage for a large view structured light scanner. So when you first open up Artec Studio, you'll be greeted with a welcome screen to see previously opened files, or this, a blank project file. We'll go into the Scan tab to check out some of the scan settings first. We could, however, jump right into capturing data while in any tab by clicking the Start button on our scanner. In the Scan tab, we have various settings on how we can capture the data. A new feature in Studio 16 is to either capture HD data for processing later, or auto-processing that HD data after each scan. Back in Studio 15, HD was released for the Ava and Leo, nearly doubling the quality of data that the scanners can capture. With this option, we can now save our HD data into our project files to process at a later time, or keep it how it was in Studio 15 by processing it right when we go into the Tools tab. There are various settings within the Advanced section of this tab, such as adjusting the color, photos captured, lighting, and using a flash bulb. But these are rarely needed to be adjusted and probably should be kept at their default settings. If we press the Start button on our scanner or click Preview, we can see data being displayed on our screen that the scanner sees. A histogram on the left shows our offset distance. It's very handy to keep an eye on it to see if you're too close or too far from an object. Pressing the Start button again will actually start capturing the data. The data being shown is now staying longer and our histogram is being displayed on our scan. We'll keep an even distance and move around the object kind of like spray painting it. And I'm keeping an eye on my computer screen, not the object, to see if I'm missing any spots in the data. The scanner is constantly capturing data. The FPS number indicates how many photos we're capturing at a time. If you stay in one spot, it'll repeat the data, leading to larger file sizes. So try to map out a path you want to take to get all the spots on the object. It'll take some muscle memory down to get how far you'll need to stand and the speed you'll need to move, but as you use the scanner more and more, you'll get faster and better and not continuously go over similar areas. When you're done capturing a scan, you can press the Stop button and see that Scan 1 has been made along with the HD capture data in pink. We captured this scan using the Geometry plus Texture mode in our settings. This lets us not only use the shape of the object, but color and shadows to keep tracking and use the texturization for the scans. If we want, we can adjust our capture settings to save processing time later or adjust how the data is gathered in the first place. Clicking Geometry Only disables the color cameras, so only the geometry of the object is being tracked. This can be handy for capturing objects that have repeating patterns in color, but can cause issues for flat expanses with little features. We can see that as we go over the seat of this chair, which is the flattest section, the scanner loses tracking and shrinks the size of it. The automatic base removal lets us create a cutting plane that removes the floor of our scan. This is handy to save time with erasing the background of an object sitting on the floor. While in the preview mode, we can see a blue grid that indicates where the cutting plane will be, and once it looks like it's in the right spot, we can start scanning. The ground can be useful for registration later, so it's purely a choice to remove the ground automatically. When we switch to the Tools tab, any scans we ran base removal on will automatically delete that ground data. Another scanning option is real-time fusion. Instead of showing a preview of the scan, we'll automatically create a mesh based on the scan data. This takes more processing power to scan with, but if you're looking to create a quick mesh from a scan, it can be helpful. We can also get a better idea of what areas we may have missed while scanning in this mode, since the mesh is generated based on the scan data we've captured. When we stop the scan, we have both the raw scan data and the fast fusion of that scan that is ready to export. When we're ready to scan another side of the part, we simply need to do a physical move of the part to a new position and just rescan it. Here, I've turned the chair upside down to get to the bottom side of it, and I'm creating a new scan while in that position. I'm keeping the same distance as before, but because these legs are extruding fairly far, I'm making sure I don't scan them too fast since I may lose tracking. For extruded lag features or sharp edges, going slower can help with the tracking. The scanner is piecing together each photo or frame of the scan similar to a panorama. If we don't have enough information to piece the frame to a previous one, then we'll lose the tracking. Having wider shots, slower movements, and having background data in areas you've already scanned significantly help with this tracking. If you lose tracking, however, you can point the scanner back into an area you've already scanned and realign and continue your scan. So at this point, we've made a couple of scans in different positions. Our scans are listed on the right side by number. If you've lost tracking for longer than a few seconds and regained it during a scan, Artec Studio will create a group of that scan, indicating that there may be two different scans listed, but they are together and can be treated as a single one. At this point, it's a good idea to save your project. Going into the File Save, we can navigate to the folder we want our project saved in and the name. This will create a new folder with the project name that holds a .a3d file and data folders of the scans. If we want to open this project later, the .a3d file is what you'd want to open. Also, if you want to send this project to someone, you'll need to send the entire folder, not just that A3D file, for them to access the data. In Artec Studio 16, project saves and opens are nearly instant because of the new data management process. Very handy for those large files with multiple scans. Also at this point, our file will autosave after each command, saving time and worry about losing project data. With our project saved, let's run the HD reconstruction on those HD scans. We can click the checkmark next to all of the HD scans to enable them and go into our raw data section of our Tools tab. Here, we can choose the ratio of normal scan frames that will convert to HD and how intense we want that conversion. The higher the ratio and density, the larger the HD scans will be, but the quality of the data will be better. Generally, having a 1/4 ratio and 4 times density works well. Each HD scan is the equivalent to about 4 or 5 standard frames in terms of information, so it's a nice balance between the size of the HD scan and usability. When the command finishes, we can group our HD scans together to help with organization. Getting a close look, we can see how the HD scans removes much of the noise compared to the standard scans, and despite the frame count being lower, we have pretty much the same amount of data being shown. We can see that one of our scans looks to have a slipped frame. This is caused by the scanner losing tracking for a moment and aligning to an improper frame. Since this is a small portion of the scan, we can likely fix it by running a registration on the scan itself or manually deleting the frames that made this section. Having background information such as the wall or ground can help with correcting these during that registration process. Raw serial registration will align each frame within a scan by the frame number. If you want to delete the frames, however, in cases where you're running a registration doesn't work, we can double click the scan itself and view individual frames that make that scan. From here, we can select on several frames at once until the issue appears and delete the frames making it. In a scan with several hundred frames, deleting a handful won't affect the end result, especially if we have that area covered in other scans too. Before we jump further into processing the scans, let's talk about some of the display settings inside of Artec. These control how the data is being shown on the screen and can be very helpful in alignments and identifying issues with a scan. On the top right, we have a small box that can expand out with a whole list of options. The backface option lets you adjust how the underside or reverse normal of a scan looks. Black will show that underside as a black color, but options such as coal will let you select through, which can be handy for enclosed scans such as buildings. New inside of Studio 16 is the transparency option, which is helpful for not just seeing through, but an outline of what's the normal face of the scan. Render mode changes how the points of the scan will be displayed. Solid is default and generally what it should be kept on. This makes it easier to select parts of the scan for alignment and erasing. Wireframe and point, however, are truer to the scan itself. If we want to get a better preview of how our mesh will look, these render modes are useful. color mode will change the color of our scans, while in texture we can see the scan with the color captured from our scanner. Scan color will change everything in a scan to a monocolor based on the color next to the name. If you are working with objects with little to no color, changing it to the scan color mode can greatly help with alignments and identifying spots in the scan that may be off. Next is surface color, which displays each frame as an individual color, helping with selecting specific frames if we want to delete or correct them. Max error will also change the individual frames, but to a color based on the error value. Error values are how far a frame is from a similar looking one. The higher the error value, the more likely the frame isn't aligned properly. As we run registration commands, these values will likely go down, but we can always delete frames with higher error values if we want. The last color mode is X-ray, which highlights frames that may be stacked on each other. If we have a spot that is infold or misaligned, they will appear brighter than the rest of the frames. After creating a mesh, I like to change my display to this mode to see if there's anything wrong with the generated mesh. The first step in processing a scan will involve deleting pieces of data we won't want in our mesh. For these scans, it will be the ground and wall around the chair. In the editor tools, we can go into Eraser to start selecting areas of our scans to delete. Going into the eraser, this will first enable all frames of the scan to be shown, then give us a few options on which selection mode we want. Since we didn't auto-delete the ground of the scan, we'll use the cutoff plane selection to highlight a portion of the ground and generate a cutting plane then. We can then delete anything highlighted red under it. For the wall, I can use other modes such as the lasso to select a bulk of information and delete it. We're going to continue doing this for all of our scans, so only the chair remains in all of them. With our background deleted, we can go into the Align tab and start matching our scans together. We can see that one scan in our panel has a blue dot, indicating it's registered and locked into place. Scans with green dots can be aligned to the registered one and rotated independently holding down Shift. If we want to unregister and re-register a scan, we can simply double left click its name. We can select multiple scans at once as well and move or lock them into place, which is handy for scans that are pre-aligned together. To help with rotation, we can double left click our scans and the workspace, which can change the center of rotation, indicated by a pink dot. When we're ready, we can start left-clicking once on an unregistered scan, and then selecting a similar area on the registered one. We don't need to be perfect with this, just the same general area works. You want to also make sure you select 3 points minimum, and that there are different heights and distances to establish an X, Y, and Z direction for the scans to match. Clicking Align will run an initial alignment, then follow it up with a best fit. I find that it's easier to switch the scan color and match based on geometry versus color, since the color of the object makes it hard to see subtle bumps of the scan. If you need to delete or move a point, we can do so by highlighting over one and then selecting it. When we're ready, we can click New Pair to make the next matching point. Auto alignment is another option we can use to match our scans together, but can take longer to finish. If you have 4 or 5 scans, this is where it starts to become more useful to use the auto align. When we're finished with our alignment, we can click Apply to save it. Now we have all of our scans prepped and ready to run some of the processing tools on them. This is a lot more automated and involves using Artec's registration and fusion tools mostly, to make sure that the scans are properly aligned for the mesh. First in our list of tools is the registration ones. As previously mentioned, these affect the individual frames within a scan, to help our scans match together much better. Rough serial registration is best run on individual scans, since they check each frame of the scan sequentially, essentially like rerunning the scan itself from the start to finish, and checking the alignments between each one of those frames. Fine registration will make minor movements within a scan's frames to help in folded sections. Both can be run just on geometry information or a combo of geometry and color. The most important registration tool, however, is global, which will be the one that you will be wanting to run above all else and even after you run the rough and fine registration tools. This will compare all of the frames within the various scans to one another, adding an extra layer of alignment between the scans. We can change the way that the frames are compared to one another as well, using our settings. New in Studio 16 is the ability to run a global registration on individual scans first, before combining them all together using the separate then collective registration mode. This will run a quick registration on individual scans, then a global registration on all of them. The rest of the settings pertain to how the frames will be used for the registration. Keyframe ratio is the ratio of frames that will be used as a reference for the other frames to align to. The higher the number, the longer the registration process is. Keeping it between 0.1 and 0.5 is recommended. Clicking the Focus on Geometry button will use some color information with the alignment, but mainly focus on using the features of the scan to match the frames. Search radius sets a limit to how far the algorithms will look for matching points to each frame. If you have a larger object with little features, increasing this can help, but if you set it too large, it can throw off the software's ability to match data together. Another new feature in 16 is that smart sampling option, which will determine the amount of points needed for the registration based on the scan itself, speeding up that process. When we're ready with our settings, we can click apply and run it on all of our scans shown. Once the registration finishes, we can see that our scans tightened up and overlapped on one another much more, which means that we are well aligned and our frames are matched to each other very well. Our error value within the scans also went down, but if we see that one scan has a higher error value than we'd like, we can go into the scan itself and delete those frames beyond a certain value that might be misproperly registered. Now, we don't have to run it with the HD data since HD reconstruction does this process, but outlier removal can be used next to clean up miscellaneous data floating around in our scan. For the Artec Space Spider or standard definition scans, this step is almost always required, and we'll look for features within a scan larger than a set value and filter that data. For example, if we want our final mesh to be 0.3mm resolution, we can set the value of this outlier removal to match. For this project, however, we'll move past this command since there's almost no noise visible within the scan due to the HD reconstruction. After running global registration and possibly that outlier removal, we can run a fusion process to triangulate the points in our scans to a proper mesh. Fast fusion is our first option and doesn't do any hole filling when creating the mesh and uses just the data within the scans together. We can set the 3D resolution of our mesh here, which will be our minimum features visible within the scan. For AVA HD scans, we can bring this down to 0.5mm resolution easily, meaning features of 0.5mm or larger will be defined well. Anything smaller, however, may be smoothed out. Smooth Fusion has some additional settings for the fusion mode, which will allow you to choose any holes to be filled when making a mesh. Watertight will leave no holes, great for making a mesh to be printed, but it may not be best for reverse engineering since it will slightly alter the data to make the hole filling better. If we want some hole filling for small portions or locations, we can choose the radius smaller than option and define what the minimum hole size of our mesh could be. The later mode will bring us in the Fix Holes tab, which we'll go over in another step. Finally, HD sensitivity can be used for HD scans to change how much noise will be used when generating the mesh. It's recommended to keep this on low or medium, but setting it higher can increase the quality of the mesh if there's little noise and you want to show features better. Once you have settings you like, click apply to start the meshing process. When it comes to fusing, I recommend spending some time experimenting with these settings since they heavily drive how the finished mesh will be. When it's finished, we'll see a new feature in our tree with a square icon shape, indicating that it's our mesh. At this point, we finally have our mesh. This is ready to export if we like, but there are a few things we can do to check the quality of the mesh, size, and orientation before exporting. Switching to X-ray mode can already give us an idea of a non-manifold spot, which may affect our prints or renders. These are often caused by two scans having an overlap from a change in shape in the part itself. There is, however, a Autopilot tab, which will guide you through the entire workflow for assistance. It will guide you step by step and have you enter general information about the part to dictate how the tools will run. It's very handy when you're unsure how to process a certain type of scan or you need to step away while it's processing. It should, however, only be used as a guide. It's best to learn what these tools do and how they run to get the best results. To recap the entire process, we first captured our data using the scanner connected to our computer, or we can import the scan data into Artec Studio for cases like the Leo and Ray. With our scans inside the software, we can then clean them by erasing background data and misaligned frames. After the data has been cleaned, we went into the Align tab and did a best fit alignment of our scans together. With the alignment done, we can go into the Tools tab and run a global registration to align the frames of our scans, outlier removal to remove any potential noise data, and then last, the fusion command to create our mesh. This is the general workflow for processing data inside of Artec Studio and can be pretty automated using the Auto tab within the Tools or Auto Alignment. Looking back, we can see that the cloth moves slightly in one scan. Since I have this spot in other scans that match better, I can delete the mismatched area from the other scans and rerun the meshing process. In our second mesh, that spot looks a lot better since it's only drawing from a specific scan now. With only our mesh shown, we can start running some post-processing commands on it. This will clean the mesh up further or make slight changes to the polygons. The first is Small Object Filter, which looks for disconnected areas of our mesh and filters them based on our setting. If we choose watertight, all but smallest is recommended, but the smaller the triangle count works better for meshes that were made using fast fusion. Hole filling will auto-patch any holes of certain perimeters. This uses a slightly better algorithm than the Fix Holes tab would, and is handy for small pockets or edges that didn't mesh well at first. The next three settings are related to changing the polygons of the mesh itself. You can check the number of polygons a mesh is by expanding out the Properties tab at the bottom right with our mesh selected. Mesh Simplification has some settings which adjust how the tools check which triangles can be fused or separated. Or if we set it to a specific triangle count, we'll try to reduce it down to that value. Fast Mesh Simplification only has a set triangle count option, and has a different algorithm that will determine how the triangles are changed, but still does a great job. The third is Isotropic Remesh, which will change all the triangles to a specific edge length, which may help with rendering and animations. The smoothing post process will apply a quick smoothing command over the entire mesh. This is done in steps, so you can keep going and applying the tool until you get to the level of smoothness you'd like. The last post-processing tool is the normal inversion, which inverts our mesh. All of these can be handy to clean up the mesh, and I'll often run these Small Object Filter and Mesh Simplification on all the meshes I export, since it makes saving and importing the mesh into other programs easier. To show off the Fix Holes tab, I'm going to first make a hole in the mesh. When we go into the tab, it will create a list of all of the holes within our mesh. Since I processed this with watertight, only the hole I made will be visible. If we select on the hole and click Fix Hole, it will do a shortest path hole fill, which may be good for flat surfaces, but not so well for corners or circles. For areas like this, we will need to break it into smaller sections. That will make the hole filling easier. First, we can adjust our edges so that way they aren't spiked and prone to mismatching. In the Bridges tab, we can create end-to-end points to split our large hole into smaller ones, which are easier to fix. I can adjust how the curvature of this bridge will be on each endpoint, making it flat, tangent, or highly curved, and how wide the bridge will be as well. For edges like this, following the seam is a good spot since it will split our hole into two halves that are flatter and easier to fill. Now, back in the main hole tab, I can select on these two holes listed and run the Fix Holes command, which gives us a better hole filling on the edge. Back in the Editor tab, we have some other tools we can use to clean up the mesh. The Smooth Brush uses a 3D selection tool to smooth out the surface of the mesh. The edge of our hole fill, which looks to have a noticeably different shape, can be smoothed out using the brush and blends everything together. Defeature is also a handy tool to remove mesh discrepancies in smooth sections. In here, you can select a patch of the mesh that is raised or lowered, such as this pattern. Once the entire feature is selected, clicking Apply will use the surrounding geometry to identify how to remove and smooth out that feature. So now we have our mesh made. It's been cleaned up with our triangle count brought down to a reasonable size. If we want to apply color from our scans or photos to this mesh, we can do so in the Texture tab. In here, we can select on a mesh we want to add color to and what scans to pull the color from. The color is added by projecting the texture frames from our scans onto the mesh, so you need to make sure that your mesh is aligned to the scans you're pulling the textures from. We can also increase the number of texture frames being captured within the Scan tab. You don't need to select on all the scans that made the mesh. Sometimes there will be scans that maybe have information deleted or odd lighting, so we can just deselect those scans from our list. For settings, the first will determine how the UV or color map is made. Clicking Preview doesn't fully make a color map, so it can't be exported, but it allows us to see how the color will look on the mesh. The Export option actually will create a UV map for the texture, and the mesh can be exported properly. The other two settings pertain to meshes that have already had color maps made, and you can reuse them to speed up the texturing process. The next set of boxes are related to the color algorithm when generating the texture map. Texture normalization will try and balance the color in areas where the lighting may have been different between one scan to another. Remove targets will remove any dots placed and distinguished already. Glare reduction will remove bright white lights from the scan or shiny materials made from the scanner. When enabling glare reduction, you'll also have the ability to suppress background colors. Finally, in paint mixing textures, we'll use surrounding colors to paint over areas that maybe the scanner didn't get a good color photo from or was hole filled. The output texture size is our last setting and determines the quality of the color. The lower this is, the more pixelated the color will be, but setting it too high will result in a very large file size. When we're ready, we can click Apply to run the texturing process and see a preview of our color with some additional sliders to adjust saturation, hues, and other color factors. If we want, we can go back into the color adjuster later by right-clicking on our mesh and our feature tree and then clicking Adjust Color. One of the coolest new features inside of Artec 16 is the ability to import photos into the software and use them for coloring a mesh. This process is called photogrammetry and allows us to have high-quality meshes from the Artec scanners and color-rich photos of the DSLR camera. To use this, we first need to import our photos into Artec Studio. It's best to take photos after each position the item was scanned in. If you happen to forget, you can always take the photo after, just placing the object back into its position. When it comes to taking the photos, you want to keep the focus at the same throughout the entire process, and have the object be as center as possible to the camera. You can then import these photos from each position separately, so you can match the photo set to a scan when aligning. Once all the photos have been imported, we want to show the mesh, which has had a color applied to it, the raw scan data, and the photo set associated to that position. Now we have a new option in the Tools tab to align the photos to the scan. The settings in here are related to how the photos will be matched. I recommend keeping them at default settings, but depending on the distance from the part the photos were taken, they can be adjusted. Once the tool finishes, we can see a preview of how the photos match to our scans by double-clicking the photo set. Back in the Texture tab, we can select on our photo sets and our mesh we want to project the photos onto and run the texturing process. We can see how the color is different due to the lighting of the room when taking the photos, and certain colors pop out a lot better. Now at this point, we've done all the changes to the mesh itself, and we can start aligning it to a new coordinate system before exporting. Back in the editor tool, we can go through a rough position to quickly establish a Z-plane of our mesh using some control points. This tool is handy for quick positioning scans for prints or possibly starting position for reverse engineering. There's also a set of transformation tools inside the editor. This allows us to make fine adjustments to the position of the mesh, or even mirror and scale it to a new size. This can be done with meshes imported into Studio as well. Other editor tools such as Defeature or color and painting can help with patch up specific areas of the mesh too. In order to show off the construction tools, I'm going to import in a new mesh of a prismatic object that's been scanned. Inside the construction tab, we have several ways of extracting primitive CAD information for reverse engineering. We can adjust how we select our data and change what type of shape we want pulled from that selection. Additionally, there are fitting mode sections to adjust how our section will adjust the primitives being made. Exact will use only triangles within our selection and have our primitive expand to all of them, which is great for selecting areas disconnected from one another. Expanding only needs to have partial selection of a surface, and uses similar surrounding triangles to define the rest of the shape. If you only have a small patch of data or don't want to highlight everything, this is the handy mode to use. Verbose is the last mode, and can be used when you have small features like cuts and bumps across a shape you want to extract. It creates a primitive based on the dominant shape of triangles. Inside of Studio 16, we also have ways to add constraints to our CAD objects. This ensures that the features extracted are properly parallel or perpendicular to one another. You can do this by selecting on one primitive, then the axis to determine which part of the primitive you want to have the constraint be based on. Then you can select on the second primitive you want to drive the constraint. When I click Refit at the top, it will rebuild our primitives based on the constraint. This constraint tool can only be done in the same session you built the primitive in, and cannot be done on them once they've exited the construction tab. Also added in Studio 16 is the ability to extract freeform surfaces from our mesh. Instead of using the fitting modes, we have ways to control the points on the surface. Once we select a portion of the mesh with the freeform shape, we can change how far we want our surface to expand past our selection using the padding slider. The number of control points drives how accurate the surface will be. The larger the number, the more accurate it will be, but may include small features like bumps and whatnot that we don't want. Order is the number of splines that will be used to build the surface. Again, the larger this is, the more detailed the surface will be. This is an amazing feature to use if you're trying to extract out a quick freeform shape to cut a CAD object inside of a modeling software. Now that we have these CAD features, we can go back into the Editor tab and use the precise positioning to do a data-based alignment on the mesh. By selecting on one of the primitives, we can assign it to an axis or where our origin will be. This gives us a perfect mesh alignment. When everything is aligned, we can export the CAD features and mesh using the file export, which will keep their current positions. Besides CAD information, we can use the Measures tab to get some 2D sketches, dimensions, and other neat pieces of information from our scan. In the Distance tab, we can select 2 spots on our mesh to do a quick linear measurement between. All of this can be saved if we want to reference it later or export the measurements. We can even do a geodesic measurement, which will follow the surface of our mesh. It just takes a little longer to process this than compared to a basic linear measurement. The section extraction is based off a cutting plane going through our mesh. We can choose a few control points or select a point and have a plane angled based on the coordinate system. The scale of the boundary box will scale our cutting plane to the entire size of the mesh. When it's disabled, it only will create a section based on our plane's size. If we want to make multiple sectional planes, we can do so as well. When we click Calculate, we'll get a bit of information about what has been extracted from the mesh. We get not only the volume and surface area of our highlighted part of the mesh, but also a 2D sketch based on where the mesh intersected with that plane. We can save this section and export it as a DXF and import it into other CAD softwares as polylines. These are excellent for being used as a reference when making proper sketch features. The last Measurements tab is for Deviation Map, which creates a 3D color map of distances between 2 meshes. If a deviation is farther than the distance, it will appear gray, so it's good to set it higher. If we want to compare a CAD file to our mesh, you need to export the CAD model as a mesh and then import that into Artec Studio. I hope you found this video helpful in learning the workflow within Artec Studio and how all of the tools work. There are plenty of cool ways you can use these tools, especially in Studio 16. For more information about specific tools, you can reach out to us or visit Artec's page and user manual on their website.